All right, today we're going big. As big as we possibly can. In fact, you might say today is our biggest lecture. Because today we're going to infinity! But not beyond. Okay, so time to talk about infinity. And actually, infinity is a really nice topic to connect into limits. For one thing, we have to understand what infinity is, but also what infinity isn't. So, first thing, infinity is not a number. And so we can't do our usual tricks like plug in infinity, because you can't plug in infinity, you can't plug it in because it's not a number. So now we have to think about, well, what is infinity? So the basic idea of infinity, you can even see it in the words. If you think of how you write the word infinity, there's the in and finity. So usually when you see the in, that means not. So it's not finity. Well, of course, finity is really, you should think of it as finite. So when we say it's not finite, what we really mean is it's not bounded. And that's the right way to think of infinity. All right, now let's get into it. Now, one thing to keep in mind, well, there's a lot of things to keep in mind, but one thing to keep in mind is when we talk about infinity, there's actually two types of infinity. Well, normally infinity, which we just write in infinity sign, well, we could really call it positive infinity and then minus infinity or negative infinity. It's actually really nice to understand that there's two types of infinities. Now you might think, well, okay, yeah, sure, that seems obvious. In some topics in mathematics, it turns out there's only one type of infinity, but that's a little bit complex. Anyway, it's a topic for a different day. So I should mention, because I'm going to mention it a lot of times over the course of our calculus classes, it's important that we actually have an orientation. So in other words, there's a left and a right, so a minus infinity and a plus infinity. Okay, so why do limits work so well with infinity? Well, what we should think of is we say, okay, if infinity is something that doesn't exist, it really means something not bounded. What we can talk about is, let's sort of talk about things which go larger and larger and larger. In other words, it grows without bound. And so that's what happens. So when we say x goes to infinity, it means that we're going to let x be a larger and larger number. So it's not like we say, oh, let's pick a number close to infinity, like 3. It's as close to infinity as any other number. What it means is we're going to take a series of numbers, one after another, that get bigger and bigger and bigger. So that's why limits work so well. In fact, you can even hear it. Did you hear that bigger and bigger? It sounded a lot like closer and closer. In some sense, when you get big and bigger, the idea is you're getting close towards infinity. Now, how might infinity show up in limits? Well, there's a couple of ways it shows up, but essentially it boils down to two possibilities. So either I'm here in the inputs, which means I'm interested in what happens as the input as my function goes to infinity. So for instance, we might have the function 1 over x. Now that's a pretty simple function. It looks something like this, whoop, and over here. So this is 1 over x. And so we can ask ourselves the question, well, what happens as we head off to infinity? Well, it looks like it's getting small. Okay, well, what, can we be more precise? Well, of course, it's getting smaller and smaller. So in some sense, this goes to 0. How about e to the x? All right, well, e to the x, very important function, e to the x. It's the exponential function. What does that look like? Well, it looks like something which has exponential growth. Well, I don't know if that really helps us narrow it down, but it looks something like this. And we see in one side it's blowing up. So, but notice something. We're approaching negative infinity. Okay, so I don't care what's happening to the right where it blows up. I care about what's happening here to the left. And to the left, it's getting, again, smaller and smaller. We might call this exponential decay. And so it's known that this goes towards 0. All right, now I said the input is one place that you might see infinity showing up. The other place is the output. So when we say the output involves infinity, that means that what's happening is that the function is getting larger and larger as you approach some value. So the classic example, again, is this function 1 over x. We can see that as x gets close to 0, you take 1, divided by a very tiny, tiny number. Well, if you take 1 divided by a tiny number, it becomes huge. And so what happens is, as we approach 0 from above, it's becoming a huge positive number. And so it's blowing up towards what we would call positive infinity. So as we come in from above, you can see there's this little plus here. We get positive infinity. Now, what happens as we come in from below? Well, again, you're taking a number 1, which is fixed, divided by a really tiny number. But here's the important thing. It has a sign. We're coming from below 0, which means it's a very tiny negative number. So 1 over a tiny negative number is going to be a huge negative number. And therefore, it's going to blow up towards negative infinity. I guess maybe blow down. Right? That doesn't sound like the right thing to say. But the important thing is it's getting big. It's getting big in size. And so, again, that minus there. So you have to be careful. Whenever you have things blowing up, you got to pay attention. Be careful. Be careful. So we want to talk about these two behaviors. So we're going to split them into two parts. What does it mean to talk about the inputs, and what does it mean to talk about the outputs? So for the inputs, what we're going to talk about, we call them horizontal asymptotes. Now the idea is horizontal, it's going left, right. The asymptotes is sort of the behavior. So the question is, in the long run, what's your behavior? So the answer is, well, it depends on the function. And if our function, as we head off towards, say, minus infinity, it gets smaller. Or maybe as we head off towards positive infinity, it gets smaller or approaches a certain value. So if our limit exists as we head towards one of our infinities, then it has a horizontal asymptote. So you have to remember, you have to check both. So you have to look on the positive infinity and the negative infinity. Now, several things can happen. One is that neither side has a limit. Or maybe only one side has a limit and the other side blows up. For example, e to the x did that. Another thing that can happen is they both have a limit. But even when they both have a limit, there's still something that can happen. So here I wrote like the kappa, like they're the same. They don't have to be the same. It could be the case as you approach negative infinity, you approach one value. And as you approach positive infinity, you approach another value. You just don't know. You have to check. So whenever we're checking for horizontal asymptotes, we have to check for two different things, the positive infinity and the negative infinity. Now, what happens? Well, one of the things that can happen is we go to something that looks like infinity over infinity or infinity minus infinity. Now, you might say, it sounds a little bit familiar. Well, infinity over infinity is similar to 0 over 0. Now, what do we mean by that? It means that it's indeterminate, which is that really hard word for us to spell. Or if you like, it's ambiguous. The problem is that we can't just cancel infinities and say, oh, it's 1 or something. No. Infinity over infinity, and similarly, infinity minus infinity, can be anything. And so you just don't know. So what does that mean? Well, when you see this, it means more work. More work. All right, well, that's okay. We don't mind a little bit of work. Same thing with infinity minus infinity. More work. So how do you do it? Okay, here's the basic philosophy. Now, depending upon when you grew up, you may have heard the expression, pump the brakes. Now, nowadays, they don't teach it at all. So if you're a very young person, you've never heard that expression. But when I was growing up, we had this notion of calling pump the brakes. Now, what does it mean to pump the brakes? Well, if you're driving a car in winter and you're on an icy road, if you pushed on the brakes, the wheels might lock up and then you lose control of your vehicle. So what the idea was, well, you don't want that to happen. So what you would do is you push off and on the brakes. So you pump the brakes. So the wheels would slow down, speed up, slow down. And what happened is it helped you gain a little bit more grip, and so it's safer, and you could bring the car under control much faster. So it was a way of recovering from a skid on ice. Now, nowadays, they don't tell you to pump the brakes. And the reason they don't tell you to pump the brakes is because modern cars are good, not our death traps that we grew up in. So in modern cars, what happens is if it senses that you might be having your wheels lock up, it pumps the brake automatically for you. But it does it hundreds, if not thousands of times faster than you could possibly do it. So what's the analogy? Well, the idea here is pumping the brakes. When I say that, what I mean is slow it down. What we want to do is slow things down. And we want to slow them down the right amount so that we can bring things to a nice and safe conclusion. So how do you slow it down? So the idea is to slow it down is to say, well, find the fastest growth. In other words, you have an expression, what's causing it to go to infinity? So what's the main driver, the largest part that's going to infinity? And oftentimes it'll be the same on the top and bottom. If it's not, just pick the top or pick the bottom. And now, once you know what's causing that infinity, we're going to take it out of the equation. The way we do that is we then divide by this rate of growth. So what is that doing? Well, what it's doing is if you've identified your fastest growth and then you divide by that, you've essentially canceled out the growth. And here's the key. We're not just dividing by something that's any arbitrary rate of growth. We want exactly the fastest rate because we want two things to happen. We don't want things to blow up, and we don't want things to go to zero. See, we want that sweet spot, between 0 and infinity. Turns out there's a lot of space there. But even though there's a lot of space, it's easy to miss. So that's why you want to say, what's the best rate of growth? In other words, what's the one that's really causing our behavior? And if we can identify that, victory, good. So we'll do some examples when we do our practice that demonstrate what's going on. Now you might want to say, well, what about infinity minus infinity? Well, okay, here's the thing. You can't really slow anything down unless by some crazy coincidence you actually get cancellation. So what we can do is we can use conjugation, in other words, sort of like that a minus b times a plus b. And if you use conjugation, what you'll end up with is it'll go to infinity over infinity, and then we proceed like we did before. So really, it's the infinity over infinity. That's the desired form for indeterminate work, because you can figure out how can I get cancellation. Similar to the idea of 0 over 0. We like 0 over 0 because we're like, ooh, let's figure out what's canceling some zeros so we can knock them out. And then like, woohoo, life is good. Same process here. What's causing the infinities? Okay, let's knock them out. Woohoo! And hopefully life is good. All right, one small detail, and this is an important thing to note. When we talk about limits involving infinity, they are always one-sided. I know it seems obvious, but we should still say it. We can only approach, say, positive infinity from below. You can't say, oh, look, here's positive infinity. I'm going to come from above positive infinity. That's not how it works. Can't do it. Be smart. Don't start. All right, now that's the horizontal asymptotes. So if there's horizontal asymptotes, you might say there should be vertical asymptotes. We control both the horizontal and the vertical. Do not adjust your dial. So what do vertical asymptotes involve? Well, vertical asymptotes are where the function is getting big. It's growing unboundedly, so towards positive infinity or negative infinity. So a limit as you approach some value. Now a could possibly be infinite, that's okay, but generally speaking it's some finite number. That's where we think of as the vertical asymptotes. It's often a one-sided limit because you can have different behaviors on the different sides. So you want to make sure it's like, oh, well, hold on, wait a second. It could be the case that they both agree, or maybe they both go down, but you may have it where they disagree. So when you're working with this, what do you do? Well, first off, you have to figure out when do we have these vertical asymptotes. And the main source of these vertical asymptotes is when you have a non-zero number divided by 0. Because what you have is something non-zero divided by something very small. So remember, when we're talking about when we're talking about limits, we're talking about as we get close. So the top is getting close to like this value for a. the bottom is getting close to 0. So it's something not in 0 divided by something close to 0, which is going to blow up and get huge. Okay, so you look for 0 in the denominator. Now, here's the part you have to be careful of. Just because I have something over 0 doesn't mean I have infinity right away or negative infinity right away. I've got to be careful. So the question is, what's the sign? The sign is the key. We're going to see the sign, and it's going to open up our eyes when we see the sign. So how do we do it? Well, what you do is you say, well, let's just look nearby. Move back a little bit from A. Move over and say, okay, now I'm not 0. Am I positive or negative? If I'm positive, I'm going to head to plus infinity. If I'm negative, minus infinity I go. And then that's it. All right, good. Well, now we're ready to tackle some practice problems. So let's get to it.